In this video, we're going to take a look at what an inverse function is. An inverse is a special function that takes one graph and it goes ahead and it reflects it over this special line that we have right here drawn on our picture. So if you can imagine drawing a point right here, say at, and we'll go ahead and do that, at the spot where we have a point at, say, 0, 2, if you were to fold your paper on this nice little line right here, the line y equals x, the inverse of this would be the reflection across it. Now notice if you reflect across it, where we end up is right here at that spot. And that spot is the point 2, 0. Now think about it for a minute. Our original point was 0, 2. Our reflection across this line y equals x is the point 2, 0. Notice that what happened is our x's and our y's switched. That's going to be very important when we're looking at equations in a little bit. The x's and y's between a function and its inverse will reverse orders. So if you have the point 0, 2 on the original function, the inverse's corresponding point would be 2, 0. Let's see if this still works with another point. So let's say we choose this point right here, and this point right here is the point 2, 5. If I were to fold my paper on this line right here, the y equals x, and I reflected this across it, it's going to end up being, instead of at 2, 5, it's going to be right here at 5, 2. Notice that those are directly crossed, and of course on our computer screen we can't really fold the paper, but those end up being reflections of each other across the line y equals x. Now keep in mind, depending on what screen you have, whether it's a calculator screen or a computer screen, if it is a wide screen, you will be stretched slightly in the horizontal direction on your view, so it won't necessarily look exactly the way it's supposed to, because things aren't completely square. You might have a bigger space between your x's than you do have your on your y's, but if everything's nice and square, then they should look like complete reflections. Now this brings us to looking at some equations. I'm going to go ahead and just freehand, you'll have to bear with me on my artwork, some equations. Let's say we had an equation that looked like this. This would be the square root of actually most likely would be kind of like a square root function. You're probably adding something or subtracting, maybe a little transformation in there. If I reflect this over, that's going to look like this. Whoops. Now notice that the reflections of each other are kind of like a half parabola. And if you remember, one thing that's important for something to be a function is it has to pass the vertical line test. Now notice this here, which is probably an equation, I just freehanded it in, but some sort of a transformation from a square root function, that does pass the vertical line test. Notice that in the reflection, it also passes the vertical line test. Now, I want you to think about something. I'm going to erase parts of this. And that was a square root function, so we were able to reflect it, but notice it looked like half a parabola. If I take a vertical line, and I'll change my color on it, say this vertical line right here, and I fold on my line y equals x, you can take some paper and do that, and I trace, notice that that's going to end up being a horizontal line. You can see that if you were to fold on this line right here, every point on this when you traced it, would land on this right here. So in order to be a function, we have to pass the vertical line test, but once we reflect over this, those vertical lines become horizontal lines. Now that's an important thing to note, because if we have to pass the vertical line test to be a function, in order for your reflection across this to be a function also, you would need to pass a horizontal line test. When you pass both a vertical and a horizontal line test, that's what's called one-to-one. In order for a function to have an inverse, it has to be one-to-one. In order to be one-to-one, you have to pass both a vertical and a horizontal line test. Now that little shape that kind of looked like half a parabola that I sketched in, that was only half a parabola, because if it had been a full parabola, it would not have passed the vertical line test and the horizontal line test. We know a parabola is a function, but if I sketch a shape that's similar to a parabola in here, notice that that shape passes the vertical line test, but it does not pass the horizontal line test. If I take and fold a paper right across this line and I reflect it over, I am going to get a shape that looks like this. Notice that that shape does not pass the vertical line test. I can draw a vertical line here, here, and here, and it'll cross in more than one point. So a parabola, even though it is a quadratic, which does pass the vertical line test, it doesn't pass a horizontal line test. So it will not have a reflection across this line or an inverse that is a function unless we restrict it. Because notice on that first one that we only had half a parabola. If you have half a parabola, that does end up passing the vertical and the horizontal line test. So we could reflect it and we could get half a parabola over there, and that would be okay. But on that, for this equation, if I had, say, this equation was f of x equals x squared plus 3, that would be this one right here. In order to make that an actual thing that we can actually reflect over this line, we would have to restrict it so that x is greater than or equal to 0. Once we do that, then you get this half of a parabola here, and that can be reflected and still be a function. Now, that brings us to a nice little check. If you are finding an inverse function, you can graph both the function and its inverse and see if they're reflections over this line y equals x. If they are not, then you would not have done everything correctly. So you would be able to go and find your error. So let's go ahead and see what we could do to maybe find an equation of an inverse. So we're going to go ahead and I'll clear out what we have here. And you'll notice that the steps that we do for finding an inverse are going to be very similar to what we talked about when we reflect over this line, that the x's and the y's switch. That's going to be key. So let's go ahead and find an inverse. The inverse that we're going to find is going to be of an equation. Let's go ahead and do f of x equals x, actually we'll do square root of x minus 2. Now, to check and see if you even have an inverse, you can go to Desmos or a graphing calculator and graph this. Make sure it passes the vertical and horizontal line test. If it doesn't, you can say no inverse exists. Now, if it does pass the vertical and the horizontal line test, which this one particular problem will, then you can go ahead and follow your steps. Now, we're going to have specific steps for finding your inverse. When we reflect over that line y equals x, the x's and y's switch. Now that's key to what's going to happen here. The first thing we're going to do is replace the f of x with a y. The only reason why we do this is to make our algebra a little easier. There's no need to really do this, but it will make our algebra a little easier. So we're going to go ahead and replace this with a y. And then because when we reflect over that line, the x's and the y's switch, you're going to switch the x and y in this equation. So we are going to go ahead and just swap those. That's going to make it so that the new equation, once we've solved, has an x in it. And then we'll be able to use the proper notation for an inverse function, which we'll see what that is in a minute. So we're going to switch our x and the y. And then after we have done that, the next thing we're going to do is we're going to solve for y. So you're going to do this just normal algebra, and the algebra is a little easier with a y in there instead of f of x, so that's why we went ahead and switched the y into, or the f of x into a y. So to solve for y, it's right now underneath that radical. Let's square both sides and get the y out of the radical. So we're going to square both sides. The square and the square root will cancel each other because they're opposite functions. And you'll have y minus 2 here. And then over here, x squared is what we end up having. Now, the last thing we need to do to get y by itself is move that 2. So we're going to go ahead and add 2 to both sides since it's a minus 2. And you get y equals, I'm going to put the y on this side, x squared plus 2. This is now the equation for our inverse. However, it is not in proper form. There is a particular notation that means the inverse of f. Remember our original function we were finding the inverse up here was named f. The inverse of f is going to be actually stated as f with a little negative 1. Now that negative 1 is not an exponent, that means inverse of f. And so to have this in our proper notation, what we're going to do is we're going to replace this y right here as inverse of f. So we're going to take that and it's going to become inverse of f of x equals x squared plus 2. Now you might be saying, well, wait a minute. This here has an x squared in it. It's going to be a parabola. And you said a parabola technically doesn't have an inverse unless we restrict it. There's something else to keep in mind. If your x's and your y's flip-flop, if you remember, domain is going to be what is okay to be in your x's. So that's going to be your x values. And range is going to be your y values. Well, if your x's and your y's flip-flop when you're doing inverses, doesn't it make sense that your domain and range would also flip-flop? Which means there may actually be an implied restriction on this inverse function that we just got. Take a look over here. If you take a look at that, that actually is not going to include all values for plugging in for x. It's also not going to have all y values for your range. On this one here, if you remember, when we were doing domain and range, that what was underneath here had to be bigger than or equal to 0. So let's find our domain for this, because our domain for the original function is going to be the range for our inverse function. So this x minus 2 in the original function has to be greater than or equal to 0. If we solve that for x, we'll find out what the domain of the original function was. And on this, your x has to be greater than or equal to 2. Greater than or equal to 2, in interval notation, we would have a square bracket at 2 because it's included, and you would go to infinity. This would be the domain on this original function. Now that tells us over here on our inverse function, our range is going to be from 2 to infinity. Now what about our range on the original function? The range on the original function is going to be the same as our domain on this function. So if we can find our range on the original function, we will have our domain on the new function that is the inverse. So our range over here, that is going to end up being what we get when the lowest value or highest value, either one, is going to be when we plug in this 2 that we just got right here for our starting point on our domain. If I find f of 2, notice that's square root of 2 minus 2, which is square root of 0. Well, square root of 0 is 0. So the range is going to start at 0, and 0 is included just like the 2, which means on our domain over here, we're going to start at 0. However, which way do we go? Well, we can determine where to go by plugging something else in that is in this original domain here. So we're going to start at 2 and go bigger. So how about we go ahead and plug in 3 and see what we get? Well, if we plug in 3 into our function, we get square root of 3 minus 2, which is square root of 1, which is 1. Notice that we're getting bigger, which means we're going to start at 0 for our range, and we're going to go to infinity. That means the domain over here is going to be from 0 to infinity. Notice the domain and range here are restricted to what we had in the original function, and that they have reversed from what we had in the original function. That means that if we graph this inverse, letting the x's start at this 0 right here and go to infinity, you will find your range starts at 2 and goes to infinity, and the only portion that is graphed does pass the vertical and the horizontal line test. So now, how can we determine if two things are inverses? I have a little hint here that you are going to use your composition of functions to find that out. Now, we just came up, we had an original function f that was square root of x minus 2, and then the inverse of that came out to be x squared plus 2. Now, we were restricted. The domain of the inverse started at 0. When we're doing the check algebraically instead of doing our check graphically, you're not going to have to necessarily worry about that too much. But we are going to do a composition of functions. If you remember, that's when you plug one function into another function. In this case, we're going to take the original function and we're going to plug into it the inverse of it. And let's see what happens. There's going to be something interesting that happens that's going to relate back to the line that we reflect over in order to get these. So on this particular one here, we're going to take this and we're going to plug it in right there since this function is getting plugged inside. That's going to give us the square root of x squared plus 2, that's what we're plugging in, minus 2. Now, I put parentheses in there and I made a different color just so you can see that it's plugged in. We technically do not need the parentheses right here. Whoops, my 2 back in there. But if you need to put it in there just to see that, yes, I am replacing this x right here with this function here, you can. Now, let's simplify and see what happens. Notice that the 2's cancel, and I'm left with square root of x squared. And if you square root x squared, you get x. Well, that was interesting. We took the inverse and we plugged it into the function, and we got x back. That should remind you that the line we reflect over is y equals x. So x right here, y equals that, is what we're reflecting over, and when we do a composition, what do we get? We get the x. Now, does it work the other way? Let's check it out and see. We're going to go ahead and try the other direction. So now, let's take the inverse and let's plug the function into it. Now, instead of taking and plugging that one in, we are going to take and plug this one in right here. So that's going to be the square root of x minus 2, and then that is going to be squared, and we're going to add 2 on. Notice that we took this here, which is this, and we plugged in right there. So let's simplify. First, this square and the square root cancel. That gives you x minus 2 plus 2. And then notice something. The 2's cancel, and all we're left with is x. So it actually doesn't matter which direction you go, whether you plug the inverse into the function or the function into the inverse, you will still get x back if you're checking it algebraically. So you should find that the function with the inverse plugged in equals the same thing as the inverse function with the original plugged in, and both of those will equal x if you are checking algebraically. Now, let's go ahead and take a look on Desmos, and let's go ahead and see if that's actually what happens. So we're going to put our line y equals x in here, and then we're going to put in our first function, which was the square root of x minus 2. Notice when we look at this on the graph, we are starting at 2 and moving forward for our domain. That's what we had for our domain. Our range starts here at 0 and goes up. Now, we are going to use a g instead of an inverse of f. Desmos seems to like that a little better. And we're going to do x squared plus 2. Now, notice that gives you the whole thing. But if we just start where our, notice that our range here was from 0 up, which means the domain on this green one needs to start at 0 forward. And this portion here matches this one here as a reflection across this. So the only portion of this green one you want to consider is right here. You don't want to consider anything else. Because we're only considering from 0 up for the domain here, that's going to be 0 forward, and this portion does match that portion there. So keep in mind, if you are trying to draw, especially if you're on a graphing calculator, it won't know how to cut part of the graph off, so you'll see the whole thing and you'll have to look at the original one to match it up with the other one. Let's real quick take a look at looking for an inverse in a function to see if something can have an inverse or not. These that is in a table format. These problems may seem like they're a little difficult. They're not meant to be hard. They're just worded a little weird. So it says the table below defines the function m. Is m invertible? Does it have an inverse? One way to find out if it has an inverse would be to think about it. In order to pass the vertical line test, your x's can only show up once. Well, if you reverse that and you're doing the horizontal line test, that means your y's can only show up once. So in this case, if you want to find out if you can get an inverse from the table, you look at the x's and you look at the y's, and if all of them only show up once, so all these x's are different, and then check the y's and all these y's are different, then it is invertible. And it's because if you were to graph it, it would pass both the vertical and the horizontal line test. To construct a table for the inverse, notice the m with the little -1, that's the inverse. You would basically just draw a table, and you would still have x, but you would have the inverse of x in your second row, and then all your x's and y's just swap. So your first point here, instead of 1, 0, is 0, 1. Your second point, instead of 2, 5, is 5, 2, because the inverse has the x's and the y's reversed. And so the next one would be 10, 3. The next one would be 15, 4. And the next one would be 25. So that's how you would do that. It wasn't meant to be hard. It's just kind of worded different. Let's look at the second one. The second one down here is a function named p, and we want to know if it's invertible. Well, notice all the x's show up once. That means it's going to pass the vertical line test. But look at the y values, the p of x. This 0 right here shows up twice. Because of that, it won't pass the horizontal line test if you were to plot all of these. And so this one would not be invertible because of that 0 right there. So these were not meant to be hard. They're just, make sure you be careful to what the directions are asking you.